Okay, at this stage we would like to start to measure the relationship between two different things. Let's say that one day you go back to this classroom and you observe those three kids, ages 1, 2, and 3. And you would like to test the hypothesis about their shoe size. Let's say that you wake up in the morning and you have an amazing hypothesis. You think that the older the kids get, the bigger their shoe size is. Pretty amazing, I know, but let's say that this is what you want to test. So you go back and you measure, let's call yi will be the shoe size for each and every kid. So the kid who is 1 year old has a 2 inches shoe size. The kid who is 2 years old has a 3 inches shoe size. The kid who is 3 years old has a 5 inches shoe size. Yi will be a new variable for us. At this point, we want to measure the relationship between xi and yi. Pretty easy so far. You see that the older the kids get, the bigger their shoe size is. Okay, that's very nice, but this is not very scientific. We would like also to exactly measure this relationship. All right. The first thing to measure a relationship between variables is called covariance. Covariance between x and y, pay attention, this is a function between two variables already. I will give you straight the shortcut here, is the expected value of their product, xi times yi, and then you subtract e of x times e of y. Pay attention once again, there is a difference in the order, in the sequence of things here. Over here you take the expected value of x, the expected value of y, and then you take the product. Over here you do first the product and then you do the expectation. So let's work on each and every part here. Expected value of x, this is something that we already saw. Here it is, expected value of x is equal to 2. So we write here, expected value of x is equal to 2. What about expected value of y? Once again, pay attention. Now you need to take the expected value of this column, the shoe size. How do we do expected value? It's always the same thing. It's the sum of the products between probabilities and values. So you do probability times value plus probability times value plus probability times value, only this time we measure the shoe size. So we do 1/3 times 2 plus 1/3 times 3 plus 1/3 times 5. Altogether, you can take the 1/3 outside of the brackets and you get 2 plus 3 plus 5, 10 divided by 3. Let's keep it as a fraction, it will help me later on. Altogether, expected value of x is 2, expected value of y is 10 divided by 3. 2 times 10 divided by 3 altogether is 20 divided by 3. This is only this part, the product of the expectation. Let's now work on this part, the expected value of the product. In order to calculate x times y, you go back to the table and you create a new column, you call it xi, yi. So 1 times 2 is equal to 2, 2 times 3 is equal to 6, 3 times 5 is equal to 15. Now we need to take the expected value of this column. Once again, it's the same thing, probability times value plus probability times value plus probability times value. Let's do that. 1/3 times 2 plus 1/3 times 6 plus 1/3 times 15. 1/3 goes out of the brackets. Inside you have 2 plus 6 plus 15. 8 plus 15, 23. Pay attention, 23 divided by 3 minus 20 divided by 3. Those are not the same things. You get 3 over 3, which is equal to 1. I want you to pay attention to a couple of things. First of all, when you take the product and then the expectation, you got 23 divided by 3. When you first take the expectation and then you do the product, you got 20 divided by 3. Once again, notice that the sequence or the order of the statistical function here really matters. First, we take the expectation, then we do the product. Here, we first do the product, then we take the expectation. We get different results. That's why covariance is not equal to 0. They do not cancel each other entirely. Altogether, the covariance is equal to 1. The second thing I want you to pay attention is that the fact that covariance is equal to 1, which is kind of a neat number, very small, very unique, if you want, means almost nothing. The only thing that covariance matters to us is the sign. covariance, surprisingly as it may sound, dictates only the sign of the correlation. The fact that 1 is a positive number, what it tells us is that the relationship between the two variables, xi and yi, ages of little kids and their shoe size, is positive. That's about it. But this we already knew. We knew that the older the kids get, the bigger their shoe size. That's about it. Or if you want to reverse the problem, the smaller the kids get, the smaller their shoe size. Okay? So positive correlation, what does it mean? It means that the two variables move up and down together. Not necessarily with the same magnitude, but they tend to move together, up and down. Xi goes up, yi goes up. That's about it. This is what covariance tells us. The fact that covariance is equal to 1, it doesn't tell us too much. It doesn't tell us the magnitude of this correlation. How strong is this correlation? Is it really, really strong, or is it kind of a weak correlation? The only thing that covariance tells us is the sign, that the fact that 1 is a positive number, the correlation between the two variables is positive. Just to give you an example, if, for example, you will get a negative correlation, you will see here, for example, 1, 2, and 3, 5, 4, 3 maybe. That the numbers here will come down as the numbers here go up. Negative correlation, it tells us that the two things go against each other. They move in opposite directions. That's about it. Still, it does not tell us how strong or weak the correlation is. In order to truly understand how strong or weak the correlation is, we need to standardize the covariance. This we do by calculating rho. This is the Greek letter rho, and I believe that you write it R-H-O. Rho is the correlation coefficient, and this is the way to standardize the covariance. What we do here, the formula for rho is the covariance between x and y divided by the product of their standard deviations. Sigma x times sigma y. Let's do that. Covariance between x and y, we already know that it's 1. So let's write in the numerator 1. Standard deviation of x, this is something that we already found. Let's see that. Here it is. Standard deviation of x at the bottom is equal to the square roots of 2/3. So let's record that over here. Standard deviation of 2/3. This is sigma x. What we still haven't found yet is the standard deviation of y. So let's quickly do that. Standard deviation of y, sigma of y. By the way, just in case you haven't noticed that so far, this is sigma, and this is also the Greek letter sigma. But this is uppercase sigma, and this is lowercase sigma in Greek. So standard deviation of y is obviously the square root of variance of y, which is the square root, and the definition of variance is expected value of y squared minus expected square of the values of y. So let's work on each and every part. Expected value of y squared, here it is. Expected value of y is 10 divided by 3. So 10 divided by 3 squared is equal to 100 divided by 9. Obviously, you raise by square both the numerator and the denominator, so you get 100 divided by 9. Let's work now on this part, expected value of y squared. In this case, you go to the table and you create a new column. You call it expected value of y squared. So y is 2, 3, and 5. Y squared will be 2 squared equal to 4, 3 squared equal to 9, 5 squared equal to 25. Now we need to take the expected value of y squared, which is this column. How do we do expected value? It's always the same story. Probability times value plus probability times value plus probability times value. All right? So expected value of y squared will be 1/3 times 4 plus 1/3 times 9 plus 1/3 times 25. Let's take the 1/3 outside of the brackets. You're left inside 4 plus 9 plus 25, 13 plus 25, 38. 38 divided by 3. Just to put it at the same common denominator as 9 as this section, expected value of y squared, let's multiply both numerator and denominator by 3. So 3 times 3 is 9, 38 times 3 is 114. Finally, 114 divided by 9 minus 100 divided by 9, what you get here, that this minus that is 14 divided by 9. So altogether, standard deviation of y is the square root of 14 divided by 9. Okay, let's plug in this here. 14 divided by 9. This is as far as I can go without a calculator. So in order to solve what is rho, the correlation coefficient measure, we need first to take the square root of 2/3. We need to take the square root of 14 divided by 9, take the product of those things, and then do the reciprocal, the 1 over. Once you will do that, you will get something very, very close to 0.98. Okay, like I said, at this point, I really would like to shift from fractions to decimal point, simply because this is as far as I can go without a calculator. So the answer is very, very close to 0.98. The question is, what does it tell us? So it really tells us that the correlation coefficient is, first of all, positive. We know that already simply because the covariance is positive. Pay attention that the covariance really dictates the sign of rho, the correlation coefficient. Why is that? The numerator here, this is what really dictates the sign of rho. The denominator, both of those must be positive. Sigma x and sigma y, they are the standard deviations of x and y, ages of little kids and their shoe size, and both of them must be positive. Standard deviation, by definition, is the square root of variance. Now, variance is positive. Take the square root of a positive number. It has to be positive. Just remember, both standard deviations and variance, they are always non-negative numbers. So if this is positive and this is positive, what it means is that the sign of the numerator really dictates the sign of rho, the correlation coefficient. So we already knew that the covariance is a positive number, and that's why rho has to be a positive number. That's fine. So the correlation coefficient is positive. But on top of that, rho, the correlation coefficient, now tells us the magnitude of this correlation, and the answer is 0.98. This means that the correlation coefficient is very, very strong. Why? Just remember that when we standardize the covariance, which means divide the covariance by the product of the standard deviation, we create a measure that is bounded between two numbers. Always remember that rho between any two variables, x and y, has to be less than or equal to +1, bigger than or equal to -1. Always rho is bounded between plus and -1. When rho is equal to +1, we call this a perfect positive correlation. When rho is equal to -1, we call this a perfect negative correlation. When rho is exactly equal to 0, exactly in the middle, between -1 and +1, we say that there is no correlation between x and y. X and y are random to each other. So just remember, this is perfect positive. This is perfect negative. And when rho is exactly equal to 0 in the middle, we say that the two variables are random, or they have absolutely no correlation between them. Because we got rho is equal to 0.98, which is very, very close to be +1, we understand that the correlation, not only that it is positive, the same thing as the covariance, but it's also very, very close to be +1. It's close to be a perfect positive correlation. It's not all the way there, but it's very, very close. Why is that? Pay attention. Let's go back to our table. In our story, we saw that the ages go up, the shoe sizes go up as well, but they don't go up at the same magnitude. If rho would have gotten us +1, you will see that the shoe sizes will go at the same magnitude. So if, for example, this will be 1, 2, and 3, 2, 4, and 6, I guarantee you that you will get that rho is equal to +1. Why? Because 2, 4, and 6 is just double the numbers 1, 2, and 3. But I slightly changed the numbers, and I got ages 1, 2, and 3, shoe sizes 2, 3, and 5. So yes, they tend to go up together, but they don't move at the same magnitude. That's why the correlation coefficient, we got that it is equal to 0.98 and not all the way to +1. This concludes our statistical review, and with this in mind, we can start our course.